All right, let's have a look at the sum and difference of angles. Going to derive it. Don't panic, they won't ask you to derive it, but this is just showing you where it comes from. So here's our unit circle on the number plane. So radius is 1. Any points on there, I can find its coordinates in terms of the angle it makes at the centre and its radius. If I was to do a little bit of trig, I could find the x value. X over 1 would be the cosine of beta. And so x coordinate would be the cosine of whatever that angle is. And similarly, y would be the sine of whatever angle that is. So the coordinates of P could be represented by the cosine of the angle and the sine of the angle. It does not matter where P is, that will always be true. So I'll put, well, it won't be P, I'll now call it Q. But that angle there, if I call it alpha, it doesn't matter that I'm now talking about an obtuse angle, because that will now take care of whether the number is positive or negative, because cosine of an obtuse angle would of course be negative, and the x-coordinate over here is negative, as opposed to the sine of an obtuse angle, which would be positive, and the y-coordinate would be positive. So it's just always the angle measured to the x-axis, however far around you've rotated. So Q would have cosine alpha, sine alpha. I'm interested in finding the distance between those 2 points, P and Q. Now, I can do it a couple of ways. I could do it using trig. Right? It's a cosine formula, PQ squared. The radius is 1, so 1 squared plus 1 squared minus 2 times 1 times 1. Cosine, the angle in our little triangle here would be whatever alpha is minus whatever beta is. And so I get 2 minus 2 cos alpha minus beta. Just going to leave that one there. I could also do it using coordinate geometry, using the distance formula. And so PQ squared, I haven't worried about the square root sign, just left it as PQ squared. So the difference in the x value is squared plus difference in the y value is squared. And if I was to expand that all out, I get this wonderful expression there, you'll see. But what do you notice in there? I hope. Yeah. We've got sine squared and cos squared alpha. We've also got sine squared and cos squared beta. And we know sine squared plus cos squared is always equal to. So therefore, we have 2 minus 2 cos alpha cos beta minus 2. Well, they're both PQ squared. I actually lied to you. I couldn't care less how far PQ is. All I'm interested in is these are both equal to PQ squared. Well, if they're both equal to PQ squared, they must be the same thing. So therefore, I now know 2 minus 2 cosine alpha minus beta is 2 minus cos alpha cos beta minus 2 sine alpha sine beta. So let's tidy that up. I can get rid of the 2's, divide everything by 2 as well, and get rid of the negative. And I come up with this first little formula. The cos of alpha minus beta is cos alpha cos beta plus sine alpha sine beta. You see, trig outside parentheses, it's not like algebra. I can't just expand out and say, oh, that's cos alpha minus cos beta, which probably would be our initial reaction to something like that. We actually have to use this formula. Now, I'm going to replace beta with minus beta. Okay. So cos alpha minus minus beta becomes alpha plus beta. I get cos alpha cos minus beta, sine alpha sine minus beta. But cosine is an even function. So therefore the cosine of minus beta is the same as cosine beta. Sine is an odd function. So the sine of minus beta is the same as minus the sine of beta. So let's tidy that up. And we get cos of alpha plus beta is cos alpha cos beta minus sine alpha sine beta. Very similar formulas, of course. The only difference is where the plus and the minus is. So there's a nice, easy way to remember this. I think you're going to enjoy this. Okay? I've written it in one here where I've gone plus minus, but then the sign in the middle is minus plus. So the sign basically changes. So the way we can think of it is like this. It's cos, cos, sine, sine. Cos, cos, sine, sine. Right? Cos, cos, sine, sine. Easy, cos, sine, sine. But if it's not the sine, which it's not because it's cosine, so it's not the sine, then it's not the sine. See? So plus becomes a minus, minus becomes plus. So cos, sine, sine. If it's not sine, it's not the sine. There's your formula. Beautiful. All right, let's now create a sine one. I'm going to go back to that original formula. I'm going to replace alpha with 90 minus alpha. So it becomes 90 minus alpha minus beta. It becomes cos, sine, sine. If it's not the sine, it's not the sine. I'm going to factorise here to make it a little bit more obvious. Complementary ratios. Cosine of 90 minus something is the same as... Right. So let's change those coses and sines to their complementary ratios, and I get sine of alpha plus beta is sine alpha cos beta plus cos alpha sine beta. Now, again, I'm going to create another formula by changing beta with minus beta. And again, I'm going to use the features of odd and even functions. So the cosine minus beta I can change to cos beta, the sine of minus beta. And you see what we get. Sine cos, cos sine. Or, of course, as I prefer to remember it, sine cos, cos sine, sine, cos, sine. If it's the sine, hang on, if it's the sine, it's the sine. All right? So, real easy to remember. Cos, sine, sine. If it's not the sine, it's not the sine. Sine, cos, sine. If it's the sine, it's the sine. Let's create one. We can't have a formula for sine and cos without a formula for tan. All right, tan is, of course, sine divided by a cosine. And we have formulas for sine and cosine. Say it with me. Sine becomes sine cos, sine. If it's the sine, it's the sine. Very good. And then on the bottom of the fraction, cosine becomes cos, sine, sine. If it's not the sine, it's not the sine. Yeah, simple. Beautiful. Now, here we go. Here's the thing. That's a bit hard to, a bit of a mouthful. But we're going to change it because it makes more sense to have tan in terms of tan. So I'm going to divide everything by cos alpha, cos beta. No, but look at what happens. The cos betas cancel, leaving me sine on cos, which is tan. The coses cancel, leaving me sine on cos, which is tan. Coses cancel, leaving me 1. Sine on cos, tan. So you get tan plus tan on 1 minus tan. Right? Yeah, tan plus tan on 1 minus tan. Easy. Now, let's replace beta with minus beta and see what happens. Now, this time, tan, odd or even function. Odd. Therefore, tan and minus beta is? Minus tan beta. So let's change those up. And we get, this time it's tan minus tan and 1 plus tan. So the top of the fraction matches what you're doing, and then the sign on the bottom has to be different. So I always just remember tan plus tan and 1 minus tan. And if it's a minus, then I know we'll swap the signs around. So here it is. Ready? Here we go. Tan plus tan on 1 minus tan. Okay, let's just summarize all those. If we want to expand out the parentheses with trig, we can't simply expand out like algebra. We've got to use these formulas. So sine becomes sine cos sine. If it's the sine, it's the sine. Cosine becomes cos sine. If it's not the sine, it's not the sine. And tan becomes tan plus tan on 1 minus tan. Hey, if you can remember pi to 42 decimal points, you're gonna remember, all right? All right, let's do a couple of examples. So I get a simple little question like this. For some reason, we want to expand cos 2 alpha minus 3 beta. Not a problem. Cos sine. If it's not the sine, it's not the sine. Done. Now, here's one. We got tan 20, tan 10. We've got to simplify this, but we don't have exact values for that. But if you look at it, it's actually already in the form tan plus tan on 1 minus tan tan. So it becomes tan of 20 plus 10, tan 30. That is one of our exact values. It is, of course, equal to, very good, 1 on root 3. Find the exact value of sine 15. Sine 15. Now, we've got exact values for 0, 30, 45, 60, 90, and so on. We want to create 15 out of 2 of those numbers. There are different ways of doing it. Pick one. Don't look at the sheet, that's cheating. Pick one. You could go 45 minus 30. Pick another one. You could go 60 minus 45. All right, which way did I go? I went 45 minus 30. So I can now use our new formula, sine, cos, sine. If it's the sine, it's the sine. And each one of those we do know the exact value of. So we can sub in, tidy it up, and there it is, the exact value for sine 15. Root 3 minus 1 on 2 root 2. Okay, they've told us sine alpha is 230, cos beta is a quarter. Biggest mistake here is to assume that they're talking about the same triangle, and of course they're not. It would be impossible to come up with one triangle where the angle, you get opposite over hypotenuse is 2/3, and then all of a sudden the other angle adjacent over hypotenuse is a quarter. Can't happen. They're 2 separate triangles. So what I'd like to do is to draw them up, find the third side by Pythagoras. So for alpha, the third side's root 5. For beta, the third side's root 15. And now to find sine alpha plus beta, it's just substitution after we use our wonderful new formula. Sine, which is, of course,
Sine, cos, sine. But if it's the sine, it's the sine.
Thank you. Now, we substitute in for sine alpha, cos beta, and cos alpha and sine beta, reading off our triangles. Voila. 2 plus 5 root 3 on 12. Alrighty, that's enough of me talking. 14B.